Welcome everyone. This video today we're going to talk about colligative properties. Okay. So what is a colligative property? Right. A colligative property is a property of a solvent. Okay. That depends only on the amount of solute particles added in the solution with that solvent. Okay. So colligative property is, again, some property of a solvent that's changing with the addition of solute, but it does not depend on the identity of the solute, just how much solute is added. Okay. For example, boiling point elevation, freezing point depression, and osmotic pressure. Okay. All of these things are related with colligative properties. Okay. All of these things are colligative properties, right? That there's something where the addition of a solute to your solvent causes these properties to change. Okay, and that's because all of these properties are related to the vapor pressure of the solvent. Basically, is what we'll find out. Right, the reason boiling point elevation occurs, right, is because the vapor pressure of your solvent decreases with the addition of a solute, right, which then means you have to take that thing to a higher temperature to get the vapor pressure to equal the atmospheric vapor pressure, right, which is thus causing the boiling point to elevate. Okay. So to kind of derive these things, what we're going to assume is the solute is non-volatile, right? Has no vapor pressure itself. Okay. So typically things like solids, right? Dissolve a solid in your liquid. Okay, that solid's not going to be really volatile. It's not going to have any vapor above the liquid, right? And then for freezing, okay, later, right, we're going to assume that the solvent, when it freezes, is in a pure solvent phase. Okay, so that when you freeze your solution, right, the solute like crashes out, right, freezes separately from the solvent. Okay, right. Basically, what we're going to do here, right, is just look at the change in chemical potential of the vapor phase and that of the liquid phase. Okay, with the solute added to the solvent, right? All right, so let's consider, right, I've added some amount of solute to my solvent, right? And then my solvent has reestablished equilibrium, right? So it has some vapor pressure now with the solute added to it, okay? The mole fraction of my solvent in the solution phase is given by Ka, right? And then, right, at this situation, right, things have reestablished equilibrium, so the chemical potential of my liquid phase is equal to the chemical potential of my vapor phase, and we're going to assume that our liquid obeys Raoult's law, right? I have some dilute solution, right? So the chemical potential in the gas phase, right, is just equal to chemical potential in the liquid phase, which is the chemical potential of the pure liquid, plus RT ln of Ka, right? Again, assuming an ideal dilute mixture here, right? Using the fact that the mole fraction of the solvent is just equal to 1 minus the mole fraction of the solute. B here is the solute, right? I get that the change in chemical potential between the gas phase and the pure liquid phase divided by RT is equal to 1 minus the mole fraction of the solute. Okay, and then we're going to note here, right, that the vaporization free energy change, the molar vaporization free energy change, right, is just equal to this difference in chemical potentials, right? Because again, right, this delta GM, right, GM is just equal to Gibbs free energy divided by the number of moles, which is equal to the chemical potential, right? And so this change in chemical potential, right, between gas and liquid, right, this is, right, in the gas is pure gas phase, right, because there's no solute in the gas phase, right? So this is the pure Gibbs free energy of the gas minus pure Gibbs free energy of the liquid, right, which is the change in vaporization free energy, right? Okay, and so delta G sub m, right, the molar Gibbs free energy change in vaporization divided by RT is just equal to this natural log of 1 minus the mole fraction in the solute. Okay. So using that, and then using the definition of the Gibbs free energy as H minus Ts, okay? And we're going to assume enthalpy and entropy are constant with temperature, okay? You get then this equation right here, right? Just plugging in for delta G vaporization in terms of delta H and delta S vaporization, okay? Right, let's consider the case, right, where I have no solute added, right? I just have pure solvent, right? So that boiling temperature is its normal boiling temperature, call that T star, right? In that case, right, these things, right, have to sum up to give you 0, okay? Right, so and so what I'm using this for is, right, I'm basically using this special case so I can kind of substitute out what this vaporization molar, right, this molar entropy of vaporization divided by R is equal to, right, basically, you know, solving this equation and plugging in to the equation, called 1 up here, right, okay, so setting this equal to, let's use a different color here, right. If I add this minus delta vaporization S of M divided by R to the other side of the equation, I see that equals the enthalpy of the vaporization divided by R times the pure solvent boiling temperature. And so then I plug that back in up here, right? And so then I get just that difference, the natural log of 1 minus the mole fraction of the solute equals the enthalpy of vaporization divided by R times the, you know, 1 over this new boiling temperature minus 1 over the boiling temperature of the pure solvent. Okay. So now we're going to make it an assumption here, right? That x be small. In that assumption, you can Taylor expand this natural log out to the first term to get that natural log is roughly equal to 1 minus the mole fraction, or sorry, not 1 minus, but just negative the mole fraction of the solvent, or solute, sorry. B is the solute, right? So ln of 1 minus x is roughly equal to negative x for very small values of x, okay? So plugging that in here, right, gives us negative mole fraction of the solute, right, is related with the enthalpy of vaporization of the solvent divided by R times this change in, you know, this inverse change in boiling temperatures. Then finally, what we're going to do is we're going to use the fact, okay, this 1 over difference in temperatures can also be written as this up above here, okay, right, which if we assume that the new temperature is similar to the old temperature, right, which should be a reasonable assumption that if I have, right, if I'm basically adding just a small amount of my solute, right, into my solvent, right, the vapor pressure of the solvent shouldn't change significantly and its boiling temperature shouldn't change significantly, right. If I have that, right, then this change in temperature, right, this difference in temperature divided by, you know, multiplication temperatures can approximately be written as a change in temperature divided by T squared, okay? And so plugging that in, I get this equation here, and then solving for this change in temperature, I get this general equation here, right, where the change in boiling temperature is related with R times T squared, where T here is the normal boiling temperature divided by the enthalpy of vaporization, okay, times the mole fraction, okay, you can call that this K prime B, okay. Now often we see this equation as delta T equals K B times B, right, where B here is the molality, okay, and then KB here is your boiling point elevation constant, okay, which we see is basically is related with the normal boiling point temperature and the enthalpy of vaporization for that solvent, okay, with some factors of R thrown in there, as well as some factors of molar mass and things like that, in order to convert from mole fraction to molality. Okay. So again, right, we got this boiling point elevation equation, okay, from looking at chemical potentials and how the chemical potential changes in your gas and liquid phase, right, and how it's related to a change in vapor pressure, and how that vapor pressure then affects, right, the boiling temperature. Okay. So freezing point depression, okay, it's basically the same approach. I'm not going to re-go over the exact derivation, okay, but it's the same approach, okay, as boiling point elevation. Right, the difference that you get is you end up with the enthalpy of fusion, right, and you end up with the freezing temperature, that fusion temperature, right. But that's it. That's the only difference, okay. And then there's this minus sign that gets in there, okay. So that's, oh, and I left it off on accident here. There should be a minus sign there as well, okay, right. But we get that normal delta T freezing is minus Kf B, right? Kf being your freezing point depression constant, right? B here is again the molality of your solute, okay? But yeah, otherwise, very similar derivation of for the freezing point as it is for the boiling point. Okay. And just to note, right, how you convert to get the things in terms of the solute, right? That the number of moles of B is related with the molality of B, right? So B here itself is the molality of substance B times the number of moles of A times the molecular weight of A, okay? Right? And basically, if you assume, right, that again you have the dilute solutions, the number of moles of A is much greater than the number of moles of P, what you can approximate is that the mole fraction of B is related with the molality of B times the molecular weight of A, right, which is your solute, okay? Right, and so these Kf and Kb's, right, that we just see printed in tables, right, is then given by these equations here. Molecular weight of your solvent, right, times the normal boiling or freezing points of the solvent, right, then divided by enthalpies of fusions or vaporizations, right. And so these are things that you could calculate yourself, right, given these enthalpies, right, and then the normal freezing and boiling temperature, okay, for any solvent.